Okay, so here we're gonna start taking a look at some properties of matrix multiplication. And one thing to keep in mind is that AB does not equal to BA. Okay, so the product of matrices is not commutative, so we can't just switch them around. Right? If the matrices are square, you'll be able to perform the product. But if they're not square, then that product won't be able to, it won't even be defined. Right? But just in general, it won't be equal to the reverse order of them, right? So, for example, let's take a look at just a simple 2 by 2 example. All right, let's say we had 1, 2, 3, 4, 5, 6, 7, 8. All right, and we multiply it here. All right, so here again we get 5 times 1 plus 2 times 14, we get 19, and then moving on to the second row in the first column, 15 plus 28, it gives us 43. All right, and then here in the next column from the first row, 6 times 1 plus 2 times 18, that gives us 22. And then lastly here, second row, second column, 6 times 3, 18 plus 8 times 4, which is 32, and that gives us 50. Okay. All right, and here, excuse me. Okay. And then if we reverse the order, if we get 5, 6, 7, 8 times 1, 2, 3, 4. Again, looking at that first row, first column, 5 times 1 is 5, 6 times 3 is 18, right? So 5 plus 18 gives me 23, right? Already we could see different, right? Still in the second row, first column, 7 plus 24 gives me 31, right? And then first column, second row, that's 10 plus 24 is 34. And lastly, second row times the first column, 14 plus 32, and that gives me 46. Okay, and we can see here, not equal to each other. All right, so sometimes not even defined, and in I think most cases we can assume that it will not be even the same matrix here. Now, matrix multiplication does have some properties, so it is associative as long as each product is defined, right? Associativity. Associativity. Okay, so as long as the products are defined, then this will be true. AB times C is equal to A times B times C, right? Whenever sizes are compatible. Whenever the product is defined. Okay, so let's say A is M by N, B is N by P, and then C is P by L, we'll call it. Okay, so we see here that this would be properly defined here on this side, AB, if we have N times N, and then N times P, N by P I should say. This resulting matrix would be M by P, and then C is a P by L. So the resulting matrix, since these are the same, M by L. Okay, and then we could see here on the right, B times C, N by P times P by L. Right, we can see these are the same, so the resulting matrix is N by L, and A is M by N. Right, the inner ones match, so the outer ones give us an M by L matrix. Right, so we can associate them differently, but we can't do them in any order, right? We can't switch around the order themselves, just the way that we associate them. Okay? All right. Now, there is also an identity or something that acts like a 1, right, for matrix multiplication, right? So we have the identity and the zero matrix. Okay. So the identity works just simply like when we think of multiplying it by scalars here, right? Well, we'll have here. Okay, so here we go. So we have what is the identity. So if A is m by n, right, then we do have an I by n matrix. The identity acts like the number 1 in the scalar multiplication, right? So here A times I to the n, right, is equal to I to the m times A, where we get the same number A. Right, now this identity matrix, this I sub n, is a square matrix, right? All right, and it would have to be square, right? Because we want, if A is m by n and the identity is n by n, we want the resulting matrix is A, so it has to refer back to size m by n. Right, now the identity matrix AN is simply the matrix where everything in the diagonal is 1. And then everything above the diagonal and below the diagonal is just zeros. Okay, so here, for example, I3 would be 1, 1, 1, 0, 0, 0, 0, 0. So that would be I3, right? Always a square matrix, okay? And then when you multiply it by a matrix A with the appropriate identity matrix, then you could just get the resulting matrix back here, okay? And we also have a zero matrix here, and that is when you multiply a matrix by the zero matrix, then the resulting matrix is just the zero matrix. Okay, so what that means is there exists here where we get the zero matrix, right? So here, since here we treat them like vectors, but we're talking about a matrix, right? So I think the book uses like the big 0 equals to the zero matrix. So here is just the m by m matrix, depending on what size you need for multiplication, is just filled with zeros. Actually, okay. All right. Now, another property here that we have is the idea of, so we can distribute the matrix across addition, okay? So, all right. So what we can do, well, we can't change the order of a product, right? We could, as long as, again, all products are defined, or all operations are defined here, we could distribute where this would be the same as AB plus AC. So again, when dealing with matrices, what we're going to find out is that the left multiplication and right multiplication yield different products, so we do have to keep it consistent. Here A is on the left, so the distribution would be on the left, all right? And it could also be on the right, all right? Again, all depending on how these matrices are defined, right? But when we distribute this, the product must remain on the right. CA. Okay. Now the last one, then, I mean, all these so far we've been familiar with, right? Working with real numbers. This last one here is where we can see how matrices, they're different, right? They have different properties as we've seen, right? And here is where, right, it takes kind of a bit of a surprising result. So here is when we take the transpose of a product. Okay, so what this statement says is take A times B and then take the transpose of it. Well, as it turns out, this is the same as take the transpose of A. Excuse me, back up a little bit here. Take the transpose of B and then multiply it by the transpose of A, right? Now here, this is important here, right? Because we've changed the order of operations, all right? So that's an interesting result here for the transpose where you can distribute the transpose here, right? But in order to do that, you have to switch around the products, right? Which is a surprising result because we've been kind of talking about how once we change the order of the products that you'll get a different result. Well, here, in order to perform a distribution, you would need to distribute that transpose. All right, and those are just some properties here. This idea where we kind of distribute some operation, in this case the transpose, also causes my product to switch around. It won't be the last time we see this type of pattern, right? This type of pattern will also show up when we're working with inverses of matrices.